Alright guys, I have few comments about the last video. I forgot to mention what is the homework problem, okay? So again, this homework problem is due on next Monday. You will have to do this problem, Kruskal-Wallis test 2. Use the Kruskal-Wallis test to see that the average or the median of these or you see that the distribution of these four categories are same or not. Okay, the Bartlett's test basically tests the homogeneity of the variance. Okay, the test statistic for the Bartlett's test is this: natural log of variance of it is the pool variance, natural log of the pool variance, and then times summation 1 through k ni minus 1 minus summation 1 through k ni minus 1 times ln s, the variance, natural log of the variance. Okay, where the pool variance sp square is given by this, so it is ni minus 1 times variance square for each of those samples, and then you add those. Okay, divided by n minus k, where n is the total data and k is the total number of samples. Also, the modified value of test statistics that is close to the chi-square distribution is given by b sub c equals to b over c, where c is given by that and b is given by this value. Okay, k is the number of samples, and for the critical value we use chi-square right table with k minus 1 degrees of freedom. Alright, so I want to take one example. This example is same as the first example of the one-way ANOVA, that is from the slide 6. Whether the variance of widths is the same for peaks fed on all four pits with alpha equals to 0.04. So that means when the variance are equal is the null hypothesis, not all variance are equal are the alternative. Now k is 4, that's the group, right, the number of dietes. N1, N2, N3, N1, N2, N4 are 5, N3 are 5, N4 is 4, N is the total N, sample total data is 19. The pool variance, we use this formula to find out the pool variance, is 9.3833. C, this formula, is 1.113. And some of those, we are about to find out B, we find out some of these, this value and then that value. Okay, so that is that value is 14.3558, and B we got is 0.530, and B sub C is 7.815. So we use all the formula here to find out these values. So using the chi-square table with degrees of freedom is 3 and the right area is 0.05, the critical value is 7.185. And since the test value does not fall in the critical region, we do not reject the null hypothesis. The Bartlett's test is powerful if the sample population are normal, but very badly affected by non-normal populations. Okay, when the k equals 2, if there are just two samples, the Bartlett's test is equivalent to the variance ratio test discussed in two sample test. Other test, do you remember that the comparing the two variances in the two sample test? That's when k equals 2, Bartlett's test give exactly the same value then with that test. Okay, other test for homogeneity of variance includes Leibniz test. We know that, we know the Leibniz test. Okay, we did that already, but this is also affected by the non-normal data. Generally, it is not recommended to test the homogeneity of variance or comparison of means because of the ANOVA is robust even if the variance are slightly different. So usually in the data analysis, usually if unless you go to the very depth data analysis, okay, you don't show that, just check the normality. But it is better if you show the homogeneity of the variance in all the data before or after you do the ANOVA. Okay, so here is a note. Leibniz test is an alternative to the Bartlett's test. The Leibniz test is less sensitive to the than the Bartlett's test to departure from normality. If you have strong evidence that your data do in fact come from a normal or nearly normal distribution, then Bartlett's test has better performance than the Leibniz test. Okay, 3 different methods were used to determine the dissolved oxygen content of lake water. So this is the homework problem. Okay, each of the 3 methods was applied to a sample of water 6 times with the following results. So test the hypothesis that the 3 methods yield equally variable results. So you are testing the equality of the variance here. You can use the Lebanese test, or you can use Bartlett's test. Since we have the code for Lebanese test already, so you can use Lebanese test to do this. So also this problem is due on next Monday. So the next thing we want to do is the multiple comparisons. Okay, when do we do the multiple comparison? So when you do the Anova test, and what is the null hypothesis in the Anova? Null hypothesis is all means are equal, right? And the alternative hypothesis are at least one mean is not equal. So if you reject the null hypothesis, then you can say that at least one mean is not equal from other, right? But to know which one is that mean that is not equal from the other, the Anova does not give you anything. We need to do the multiple comparisons, okay? That's what it is saying. So if there are k samples, then there will be k times k minus 1 over 2 pairs that we can compare, right? If all samples have the same size, 2k test, also known as the honestly significant different test, is an excellent, let me circle this, is an excellent way to compare the means. To apply this method, we need to arrange the number of all sample means in ascending order. Then we find the pairwise difference between all the means xi bar minus xj bar. Then we find 2k test statistic given by q equals to xi bar minus xj bar over standard error, where the standard error is s squared over n under the root, and s squared equals to s squared w is the mean square error defined in Anova. It has a lot of work, but it is still doable by hand, but I will show you how to do by both hand and in R. To find out the critical value, we use Q distribution table for 2k test with n minus k and k degrees of freedom and alpha. So for H0 is Hi equals to Hj, we reject H0 if Q is greater or equals to the critical value. We also use the right tail test for the 2k test. Okay guys, so these are the steps. H0 is mu b equals to mu a. B is the bth sample, a is the th sample, so there may be more than one samples there, right? So you will have to do for each of them. And versus h1 is mu b not equals to mu a, where mu a is the mean of sample A and mu b is the mean of sample B, and so on. To find the test statistic, find the mean of each sample and sort them in ascending order. Then find the pairwise difference of the means and find the standard error given by this, where s squared equals to mean square error s squared w within the group, okay, in Anova. So finally find the test statistic using this formula. Find the critical value using the 2kq table. There is a separate 2kq table, you can find it online with n minus k and k degrees of freedom and alpha. Also our textbook has 2kq table there. For H0 is Hi equals to Hj, we reject H0 if q is greater or equals to the critical value. So if you want to see one example of the 2k test by hand, so you can look at the our textbook, page number 231. Okay, that's our textbook. Look at those that example. Testing all pair means with unequal variances. In this case, Games and Howell proposed the use of Wells approximation to get the standard error as that value. If you know that the two population variants are equal, use 2k Kramer test. So there are so many tests, right? But the 2k test is the mainly you need to know how to compare the pairs in if there are more than one pair there, right? So pairwise comparison, or we call multiple comparison. Okay, other methods for multiple comparison is Duncan test, Student-Newman, Kewell's test, Don or Benferroni least square difference method, and so many others. So this is Donnet test. This is similar to the multiple comparisons, but sometimes we are interested in comparing the mean of one group called control group to the mean of all other k minus 1 group. Donnet provide an excellent procedure for such testing, okay, for only one. So this is also the multiple comparison, but what you do is you fix one of them, that is the control group, and then you compare with the, for example, if one pig is given one diet that is like traditional diet and all other pigs are given different diets, you compare the traditional diet to each of those different diets. So this type of problem can be done using the donut test. So this is basically the methods to do the donut test, okay? And there are multiple non-parametric tests for the multiple comparisons, okay? You can look at this, you can read these for multiple comparison of the means, multiple comparison for the non-parametric test, okay, and multiple comparison of the variance. But I want to summarize all these things of the Anova in the last 2 slides, and then after that we will do the two-factor Anova. But I will show you how to use 2K test in R, okay guys? But let's go over this slide. Sample should be, what are the things to know? Sample should be randomly selected. The sample size are roughly equal. In extreme cases, largest sample size should not exceed so the ratio of the largest size divided by the smallest size should not exceed 1.5. That is the extreme case for the Anova, okay? The dependent variable should be quantitative. That should be a number, right? So if the response variable are in Likert scale means, do you remember that because in the hospital what they do is, if you have a very no pain, then you give like 0 pain, right? If you have a little bit of pain like this, and then you give number 1 pain, right? Number 1 pain, and so on. So this is the Likert scale. Basically what they do is they change the categorical data into the numerical, okay? So the pain scale is the Likert scale. You give number to the amount of the or the extent of the degree of the pain, okay? That's called the Likert scale. So the dependent variable should be quantitative. If the response variable are Likert scale, we use non-parametric test. In that case, you use the non-parametric test. Some people argue that if the Likert scale has more than 5 options, we can use Anova. No outliers or extreme values within the groups. If there is an outlier, you can replace it with less extreme value, or transfer the data into other form, or delete it, or proceed under the assumption that the outliers will not affect the analysis. Okay, independence of sample. The participant in one group should be only in that group. It should not have any influence to the probability of the others. Normality, the response variable, should be approximately normal. The data should be normal, or normal or approximately normal, right? For bigger sample size, Anova is robust for violation of normal. If the sample size is big but the data is not normal, you are okay to use that. Normality can be checked by using the Shapiro-Wilk test. If not normally distributed, then you can use non-parametric test, okay? Anova is robust of simple violation of normality. So another is the homogeneity of variance. If the data has severely non-homogeneity of the variance, there is a chance of type 1 error. Homogeneity can be tested using several statistical methods. If you do not have homogeneity, you can make it homogeneous by transferring the data into other form, or declare that your data do not meet the assumption. Alright, that's all. So the let me see if I have so I do not have a homework problem from this section, from the multiple comparison, but I'll give you one example in R. But in the project 3, I will give you a question from this part 2, from the multiple comparison. Let me show you this multiple comparison. When you reject H0, you may be interested to see the pairwise comparison and find which population has been different from the other, okay? This is called the multiple comparison. There are several methods for that, and the 2K test is one of those. So what I'm doing here is I'm taking the plant growth data. What is the plant growth data? Let me show you that. So plant growth data, plant growth data. Let me run this plant growth data. What you get is, that's the plant growth data, right? There is a control group, there is treatment group, treatment 1, treatment 2 group. Now what I'm doing here is I'm doing the Anova. So this is what I got for the summary of the Anova. I don't need the other things. Just a summary says that we reject the null hypothesis, right? So meaning that the mean of the control group and treatment 1 and treatment 2 group are not the same. But we want to know which one is different, right? That's why we use the 2K test. So I gave a name 2k.test, but you can give any name there. So this is the function 2khsd, and then plant.av, you put that thing here. Okay, so let me run this. It will give you the pairwise comparison 2k test. You see that treatment 1 and control, you compare those two. What is the p-value? It is greater than alpha, so they have the same mean. Treatment 2 and control, we have the p-value greater than alpha, so they have the same mean. But treatment 2 versus the treatment 1, they have the p-value is less than alpha, so they have the different mean. So this is how you do the pairwise comparison, or we call multiple comparison. Okay guys, thank you.